So it's my pleasure.
But
Let me start by, I would like to introduce Professor Ghaith Hiary, who is an associate professor of mathematics at the Ohio State University in Columbus. Professor Hiary received his PhD in mathematics from University of Minnesota, and then he did his postdoc at IAS, University of Waterloo and Bristol. Professor Hiary works in analytic number theory and computational mathematics. So it is our pleasure to have you speaking to us today about how to verify the Riemann hypothesis for the first 1,000 zeros.
all right, thank you very much, Wissam. And I would like to also thank Professor Jihad, Tuma and Kams, and AUB for inviting me. Today's talk involves a lot of history about computations with the Riemann zeta function and about the primes. My goal is not to get technical, but to give an idea of why it was interesting to compute with the Riemann zeta function. So to start the story, going to go back to Euler. So Euler considered the prime numbers and their distribution, right? And he counted the primes, tabulated them. So here's a table of the primes or counting of the primes that I found in unpublished notes that were included by Boniakovsky and Chebyshev. And this table,
sorry, guys,
yes.
the page is not moving. It did the same thing it did last time. So I think you need to share it.
Okay. Sorry. Okay. Right, so let's try again. Is the page moving?
Yes, now it's good.
Great, so let me restart about the slide here. So this is a table I found by Euler where he's counting the prime numbers, right? So the first column is n, so he's counting the primes less than or equal to n. And then he classifies actually not only the primes, but classifies the integers less than or equal to n that are product of 2 primes and the integers that are product of 3 primes and so on. So he classifies these into classes that he calls alpha, beta, gamma, and so on. So alpha would correspond to the number of primes less than or equal to n, except that he included 1. It was common to include 1 among the primes or to count it among the primes. So as an example, if n is equal to 8, you have alpha is equal to 5. So that would be the numbers 1, 2, 3, 5, and 7. And beta is equal to 2, and gamma is equal to 1. And then if you sum over all the classes, you get the total is equal to n. Right, so this kind of tabulation allowed Euler to consider the distribution and the frequency of the prime numbers. And what he observed is that the law of the progression of the prime numbers is that they appear less frequent as n increases. So if you look back at this table here, if you consider the, when n is equal to 1024, so Euler is going in powers of 2. When n is equal to 1024, and you take the fraction of the number of primes less than that, which is 173, including 1, you consider this fraction, and then you consider the 98 over 512, which is the previous row in the table. And you see that these ratios are decreasing as n increases, right? So from that, he said that the primes appear to be less frequent. But he also said that the behavior of the primes is very irregular. He gave an example that when he counted the primes in blocks of 100, for example, there would be between 200 and 300, there are 16 primes. Yet between 400 and 500, there are 17 primes, which is more. So the frequency of the primes goes down, but it's not regularly going down. And also he says from 79,700 to 79,800, there are 3 primes, yet for a larger n, between 90,000 and 90,000, there's a typo here, there's an extra 0, 90,100, there are 13 primes, right? So it's not like that doesn't seem that there's a simple law that describes, the frequency of the primes, even though generally speaking, they appear to be less frequent as n goes, as n increases. Right. And by the way, if there are any questions at any point, feel free to interrupt me. I'm happy to answer anything. Right, so this kind of tabulation of the primes gives rise to the question, did Euler know about the prime number theorem? And I didn't find like definitive evidence that he knew. I've been looking through a lot of, the stuff that he's been writing, but for sure he knew about the Euler product, which appeared, as far as I could tell, for the first time in 1737. So this would be Theorem 8 right here. He wrote the Euler product a little bit differently. This is the standard way of writing it. I don't know if you can see the mouse pointer I'm using. Hopefully you can. But I'm pointing to the standard way here of writing the Euler product, and this is the way Euler wrote it in 1737. And from that, he did use that, he looked at the divergence of the Euler product when n is equal to 1, so he used the variable n here. And from that, he did use that the primes are, they are infinite, but they are infinitely less numerous than the whole numbers, which corresponds to his earlier observation that they become less frequent as you go higher and higher. But at the same time, the prime numbers are infinitely more numerous than the squares of the whole numbers, because as he had famously computed, the sum over the squares of the whole numbers, actually, starting at 1, is finite. It's equal to pi squared over 6. Right. So Euler didn't, at that point didn't seem that he had access to our, he didn't use the standard language that we use to express such things. Instead, things like this would appear. He would look at the sum 1 plus 1 plus 1 to infinity, and he denoted that by infinity. And then looked at the harmonic sum and said, this is infinite, but considered it to be kind of a smaller, say, infinity, and denoted it by log of infinity. And then when he looked at the Euler product, he did use that the sum over the reciprocals of the primes would be diverging, like log of infinity. So later on in his writing, actually, he started to use more standard language. So for example, by 1776, if you look at this part here, he is expressing the divergence of the harmonic sum using standard language, saying that the harmonic sum, if you sum up to x, diverges like logarithm of x. So L of x here is logarithm of x. Right, so he had an understanding of like an asymptotic sort of behavior, though, earlier in 1737, he didn't use that kind of language. right? Now, Euler's class papers were about 1783 when he passed away, and after this there wasn't much, say, notable progress on the theory of the prime numbers. The first kind of important advance was by Legendre. Legendre also recognized that the prime numbers are extremely irregular, as Euler had said. But he proposed a formula to count the number of primes less than or equal to x. And the way he obtained that formula or conjectured that formula is using numerics. By tabulating the primes, he went much farther, up to 1 million. Actually, he didn't, he relied on prime tables by other people, although he did his own computations too. And based on this kind of tabulation of the primes, he proposed that the number of primes less than or equal to x is equal to x over log of x minus 1.08366, which is a strange looking constant, right? Right, so the tables that Legendre used were, generally accurate. They were off maybe by 1 to 6, but up to about 70,000, they were completely accurate. And then to kind of display the usefulness of his formula, he used it to approximate some products and sums over the primes. For example, he approximated this product over the primes here, and the sum over the reciprocal of the primes. He excluded 2 in this sum. And for example, he calculated the constants in the formula for the sum over the reciprocals of the primes. Yeah, so there's a typo here. The 1 should not be there. Okay. And then at the end of this paper, where he conjectured this formula for the number of primes less than or equal to x, he wrote that it was remarkable that one using basically calculus and his formula can deduce some essential properties of the prime numbers, such as sums over them or products over them. But at the same time, the Legendre formula looked a little bit strange. I mean, the constant that appears in there, it seems like a random looking constant, and there were doubts about how accurate that constant is. Even in 1838, just like 8 years after Legendre published that conjecture, Dirichlet wrote that probably Legendre's formula is not exact except in the leading term, and then the true limit is given by this sum here, which is equal to the logarithmic integral, Li of x, which is usually what appears when, which is what appears in the usual formulas for counting the primes less than or equal to x, right? The issue with the strange looking constant here, some people try to kind of explain this. So for example, Drac in 1844 tried to relate this constant to some exact quantities involving pi and rational numbers. But still, this was based on just a numerical computation, and there was no theoretical reason behind it. Right? So I try to, one thing I think maybe helps to understand why Legendre conjectured this is to look at the number of primes less than or equal to x in the range that he considered, which is for x less than or equal to 1,000,000. So if, as usual, we denote pi of x by pi of x, the number of primes less than or equal to x, then we look at the difference between the Legendre approximation and pi of x and graph that, we get something like this. And also here I graphed the difference between Li of x and pi of x, which is the orange curve. And you can see that the Legendre approximation behaves in a much more intuitive way in that it's oscillating about 0. Basically, the error is oscillating about 0, whereas the error that comes from Li of x is, quite positive and remains positive. So this might have made the Legendre approximation look much more attractive because it's behaving in this way and it's oscillating about 0. Actually, if you go much farther than 1,000,000, for x much greater than 1,000,000, you can see that the Legendre approximation starts getting worse and worse. So this is the second graph here. So by the time you get to 10 million, the error in Li of x, which is this point, is quite a bit smaller than the error in the Legendre approximation. But Legendre didn't have access to such, to counts of primes for such large values of x. Right. And it turned out that Gauss also did some tabulation of the prime numbers up to x is equal to 3 million, which he wrote about in a letter to one of his students in 1849. And based on these computations up to 3 million, he conjectured that pi of x is well approximated by Li of x, and that he didn't speculate which one is the right approximation, whether it's the Legendre approximation or Li of x, but he commented that the errors in the Legendre approximation, even though they are smaller, they are growing faster than Li of x. So basically here, he's referring to this portion. So the errors in the blue curve, the distance from 0 here is smaller than the orange curve up to, say, 1,000,000 right here. But the size of the blue curve is growing faster than the orange curve. Right. So, it wasn't, at this point, it still wasn't resolved what is the correct approximation to use for counting primes less than or equal to x. This was resolved by Chebyshev in around 1851, 1852. He proved that the Legendre approximation cannot be correct, that the constant that appears there cannot be correct, and if one were to put a constant, it has to be equal to 1. Right? This was a big advance because up to that point, even though we had many conjectures and formulas for the, about the primes, none of them were proved. So the Chebyshev result here is the first kind of real progress in the theory of the primes. Right? And in addition to kind of proving that the Legendre formula cannot be correct beyond the leading term, he also gave reason to believe that the Dirichlet and Gauss approximation given by Li of x is much more likely to be accurate, or is the much better approximation for counting primes. Right, and very importantly, he obtained lower and upper bounds on pi of x, right? And basically, the result that you obtained allows you to calculate pi of x with an error which is about, relative error, which is about 10%. So the constant that appears in the upper bound is about 1.10, and in the lower bound, it's 0.92. So within 10%, you can, relative error, you can compute pi of x using this Chebyshev result. Right, and as a consequence of this, Chebyshev was able to prove the Bergnard Postulate, which is that when n is greater than 3, there is always a prime between n and 2n minus 2, which was stated a decade earlier, and it's kind of a very intuitive statement. It must be true, but it could not be proved until the Chebyshev work. Right. Then we come to the Riemann formula. So the distribution of the primes still remained mysterious. Euler and Legendre commented that the primes are very irregular, they have many anomalies, and there was no clear explanation for the strange behaviors of the primes. So in 1859, that's when Riemann published his paper, where he explained that the strange behavior of the primes can be entirely understood through some new sequence of numbers, which are roots of or zeros of the zeta function, zeta of s, which is for when real part of s is greater than 1, is given by an Euler product here. And the way this explanation worked was through this formula here. This is an exact formula basically for the pi of x. Now, there's a little bit of difference in notation here. Riemann used f of x to denote pi of x, right? And then this little f of x is related to pi of x by Möbius inversion, right? So the formula that appears in Riemann's paper is for little f of x, but then from that you can get an exact formula for pi of x. And here you see that the leading term of the formula is given by the logarithmic integral, and then there's a sum which is over alphas. The alpha here are referring to the complex zeros of the zeta function. Okay. So the zeta function had been studied before as a function of real variable by Euler and Dirichlet. So the important advance here was to study zeta as a function of a complex variable, which is what opened the connection to these complex zeros of zeta. The Riemann in his paper proved the functional equation for zeta, which is given by this form here. So one defines C of S, which is the completed zeta function, and then with this definition, the functional equation takes a simple form, which is that C of x is equal to C of 1 minus S. And this functional equation actually appeared already in Euler's work in 1749 in this form here. So S here is an integer, and this is basically the statement of the functional equation. Right? And there are some other notational issues if you're, which is that Riemann used pi of s instead of gamma of s to work with the gamma function, and there's a relation between these two functions. Gamma of s plus 1 is equal to pi of s here. And also the function he denoted by c of t is actually nowadays denoted using this symbol here. And the c is reserved to denote the completed zeta function. But you know, in 1859, the Riemann paper was quite novel and mystified mathematicians at the time. The parts where he proved the analytic continuation of zeta and the functional equation were understood, but then many other parts of his paper were not. Right, so for example, the existence of trivial zeros of zeta at the negative even integers, that there is a pole of zeta at s is equal to 1, and that all the complex zeros of zeta have real part between 0 and 1. These were all understood, but things like the infinite product formula for C of S and his conjecture, or what's called nowadays the Riemann hypothesis, which is that the complex zeros all lie on the critical line, which is the line determined by real part of S is equal to 1/2. So these two things were not understood, or were out of reach. They needed a lot more work. Right, but the basic kind of picture for the zeta function, which is this picture here, and this picture assumes is placing the complex zeros, the non-trivial zeros of zeta on the critical line, were understood. Right. So Riemann published his paper in 1859, and for the next 20 years, there was little progress on, clarifying his work. Even 26 years later, Stieltje wrote to Hermite. They had a long correspondence about Riemann's work. He wrote presumably in 1885. The letter I found was undated, but I think that's when it was written, saying that he could not understand how Riemann obtained his formula to count the number of complex or non-trivial zeros of zeta up to a given height on the critical line. So this formula that Stieltje is referring to is this formula. So n of t denotes usually the number of complex zeta zeros with ordinates less than or equal to t. So if you imagine the critical line and you go up the critical line, you go up to t, then you count how many zeros you have up to that height. So Riemann had stated that this function n of t satisfies this approximation or this asymptotic formula, but did not give a full proof. And the sketch that Riemann gave in his 1859 paper, it was, Stieltje was writing to Hermite that he couldn't understand it. And later Stieltje gave an explanation and wrote an essay to kind of clarify Riemann's derivation of this formula for n of t. Stieltje also had some other difficulties in Riemann, but this was one of the first major ones he had. Right, and the other thing that Stieltje realized, which he wrote in a letter to Mittag Leffler in 1887, is that one cannot deduce from Riemann's exact formula for pi of x that basically the prime number theorem, which is that limit as x goes to infinity of pi of x over li of x is equal to 1. So he said that in order to deduce that, we have to know that there are no complex zeros of zeta on the line real part of s is equal to 1, right? Which was not proved in Riemann's paper. And he also wrote that it was difficult for him to prove rigorously the infinite product decomposition for the zeta function that appeared in Riemann's paper. Right, and Silje was looking at this. He was still under 30, doing his actually some sort of undergraduate studies, and he thought he had a, after looking at Riemann's work, he thought he had a proof of the Riemann hypothesis, which he announced in a note in 1885. And his proof was based on studying the Dirichlet series for 1 over zeta s. So here the Dirichlet coefficient would be mu of n, which is the Möbius function. So ultimately, Silje withdrew his claim that he could prove the Riemann hypothesis, but still claimed that he could show that partial sums of the Möbius function would be bounded. If you sum up to n, then the sum would be bounded by n to the 3/4 plus epsilon for any positive epsilon, which would imply a zero-free region for zeta. So this would imply that there are no complex zeros of zeta with real part greater than 3/4, which would be a major result. He never gave details or published, a proof about this, but yeah, there were, other actually claims for proofs of the Riemann hypothesis. There was another one made by Jensen in 1899. So, faulty kind of claims of proving the Riemann hypothesis were floating around in the 1880s and 1890s. But things started to pick up, and the main obstacles in Riemann's paper were starting to be proved and explained. So the first one was Hadamard in 1893, who proved the infinite product decomposition of zeta that appeared in Riemann's paper. This showed that there are infinitely many complex zeta zeros. Then von Mangold in 1895 proved the Riemann's formula for n of t, which counts the number of complex zeros on the critical line of height less than or equal to t. And von Mangold proved this with an explicit error term. And he also simplified Riemann's derivation of the exact analytic formula for pi of x. And eventually this period in the 1890s culminated in a proof of the prime number theorem by, that was in 1896 by Hadamard and Poisson. Right, so this was a confusing period, between some theoretical difficulties with Riemann's paper, some faulty claims of the Riemann hypothesis. So there was interest in actually looking at, these mysterious zeros of zeta, these complex zeros that could explain the mysterious behavior of the prime numbers and their distribution. Things like that there are infinitely many non-trivial zeros of zeta on the critical line or in the critical strip, they were not easy to prove. I mean, this was really proved in 1893 only by Hadamard. So as far as the math world knew at that point, the sequence of non-trivial zeros of zeta was a complete mystery. It seems that the first attempt to kind of get, a hint or to numerically approximate these zeros was by Silje in a letter in 1887 that he wrote to Mittag Leffler. And this is the picture I have here is the part of his letter where he's saying that he used the infinite product for the zeta function and some serious expansions, and approximated that the ordinate, so the ordinate of the first zero of zeta is about 14.5. So as far as the math world knew at that point, that was the first attempt to numerically approximate a zero of zeta. Now, it turned out, and this was not found until 1932 by Ziegel, that Riemann actually tried to approximate zeta zeros using a formula called the Riemann-Ziegel formula. And he approximated the first zeta zero by 14.1386. But this was not found until 1932. So Stieltje presumably didn't know about this. Okay, so short of actually numerically approximating these zeta zeros, there were attempts to bound the height of the first zeta zero on the critical line. And there was an interest because you could actually, if you have some knowledge about these zeros, you could maybe use it to compute pi of x using Riemann's exact formula. Right, so Jensen in 1887, using again the infinite product decomposition of the zeta function, proved that the first zeta zero, and actually he kind of also assumed the Riemann hypothesis in his derivation. He proved that the first zeta zero has height at least 6.56. And he said he could generalize his method so to show that the height should be at least 8.4. The way he did that is, if you look at this picture here, on the one hand, he could calculate this sum over the non-trivial zeros of zeta and get a numerical value for it, which he could compute directly. And this numerical value involves the polygamma function and Euler's constant. And using positivity from this, he could deduce that alpha 1 has to be greater than 6.56. Otherwise, the sum over the zeros on the left side will be larger than the right side. Right? Then, I mean, I have to say that Jensen's bound on the first zeta zero was not really rigorous at that point because he used the infinite product for zeta, which was not proved in 1887. He appeared to assume the Riemann hypothesis. So this was, there were some things, some incomplete details. The first complete lower bound on the first zeta zero seems to be by von Mangold in 1895, who proved that the height of alpha 1, the first zeta zero, has to be at least 12. And he used a totally different method, which involved the argument principle from complex analysis. So he didn't use these Taylor expansions that Jensen used. Instead, he just directly looked at the argument, change of argument of zeta along a suitable path. And he concluded his paper by speculating that maybe it's not impossible to have a zeta zero of height between 12 and 13. We know that there's no such zero, but all he could say with certainty is that the height of the first zeta zero has to be between 12 and 53. Okay, then there was a an important advance. It wasn't major, but was an important advance in the same year by Graham in 1895. He developed this method involving series expansions with the logarithm of the infinite product for zeta, and but instead of expanding basically at the edge of the critical strip, he expanded at the center of the critical strip at t is equal to 0 here. He managed by doing such expansions to get an approximation for the first 3 zeta zeros. And this screenshot here is where he's giving his approximations. So he approximated alpha 1, the first zeta zeros, by 14.135. Alpha 2, the ordinate, or the second zeta zero, by 20.82. And he also had an approximation for alpha 3. So he was, doing these approximations. His method was, it's difficult to control it because the coefficients, these sums over the zeros, which take this form here, they decay very rapidly with k. You need high accuracy to deduce information about the alphas from values of these sums. And also his computation did not verify the Riemann hypothesis. He basically assumes that the alphas are real, and that's how he ends up getting these approximations. Right, but this was beyond what has been done before. Now, the next big step was to introduce the Euler-Maclaurin summation formula for computing with zeta. Now, this formula actually, again, goes back to Euler. And here's the first place in this picture I have here. As far as I could tell, this is the first place where this formula appears in Euler's work. And if you look at this part, you can see the Bernoulli numbers, but divided by some factorial factor. Right, so this Euler-Maclaurin formula is very useful summation formula. Actually, Graham, in his first attempt to approximate zeta zeros in 1895, he cited the Euler-Maclaurin formula, but for real variable. Apparently, he didn't use it to approximate zeta because he doubted that the formula would work when the variable is complex. But then when in his second attempt to approximate zeta zeros, which was in 1903, he wrote that nevertheless, he decided to give that a try, and he was struck with the ease, by the ease with which it succeeded. So he is commenting that this method using the Euler-Maclaurin summation formula worked much more nicely than his earlier complicated method involving the infinite product and series expansions of the logarithm of the infinite product. Right? But before I get to Graham's second attempts, which was in 1903, there was in the same year another attempt to approximate zeta zeros, which was by Lindelöf. And Lindelöf used a formula which actually reduced to the Euler-Maclaurin summation formula to approximate the zeros of zeta. His method is that by Riemann's work, we know that this function, pi to the minus s over 2, gamma of s over 2, zeta of s, that this is a real function on the critical line. So if you look at the arguments of this, it has to be 0 or pi modulo 2 pi on the critical line. right? So to separate zeros of zeta on the critical line, you just need to compute omega modulo 2 pi with an error less than pi over 2. And if then this way you can detect if the sign of this function has changed, from a given value of t to the next given value of t. And if it changes, then if the sign changes, then you know that there's a zero in between. And to compute, so the difficult part about computing omega is to compute the argument of zeta s. The argument of the gamma, you could use the complex form of the Stirling formula, and this factor is easy to compute, right? So to compute the argument of zeta on the critical line modulo 2 pi, he used the Euler-Maclaurin formula. So he just looked at the real and imaginary parts and used those to recover the argument modulo 2 pi. And this picture here is a table that shows the values of omega that he obtained. So you can see, I mean, he's writing omega in degrees instead of pi, in terms of pi. So you can see the values of omega are kind of fluctuating between about 180 degrees, so pi and 0. Right? And from this, he gave intervals that would contain 10 zeros of zeta. So the first zero he wrote should be between 14 and has height between 14 and 14 and a quarter. And then for the higher zeros, he just gave them, in an interval of the form k up to k plus 1. So an interval of length 1. Right, so he simply basically used his methods, stepping through the integers. So y here would be our t. He used y instead of t. And let y step through the integers. And then whenever he detected a sign change, he knew that there's a zero in between. These computations, though, did not verify the Riemann hypothesis. I mean, in the sense that he didn't know that he found all the zeros. So he went up to 50 here. He didn't know that he found all the zeros of height less than or equal to 50. Right? And he didn't know whether the zeros he found were simple or not, so multiplicity 1 or not. You could say that they are odd multiplicity, but didn't know that they are simple. So in this, I mentioned Lindelöf's computation 1903. In the same year, Graham also published his computations, which were his second attempt. These two things came at about the same time. And actually, Lindelöf wrote in his paper, he learned about Graham's computations just a few days before publishing his own. But up to that point, before I even get into Graham's second attempt, up to this point, there have been 4 approximations of the first zeta zero. So the first approximation was by Stilge in 1887, which gave 14.5. Then Graham in 1895, which gave 14.135. Lindelöf in 1903 said the first zero is between 14 and 14.25. And as was later discovered in 1932 by Siegel, Riemann had approximated the first zero by 14.1386. And here's the true value, the first zeta zero. And so looking at these numbers, Graham was closest. Graham's second attempt, actually, he managed to get much better accuracy. So here's a list of the first 10 zeros that he computed. You can check that the values he's giving are accurate within plus minus 5 times 10 to the minus 6. So these are the most accurate computations to date at that point, so by 1903. right? And in addition to these first 10 zeros, he gave rough approximations for the locations of the next 5 zeta zeros. You know, not to within 10 to the minus 6, but you know, to within you know, 1 decimal digit. But importantly, he also verified the Riemann hypothesis for the zeros he computed. So the way he verified it is he went back to his first attempt, which involved computing highly accurate values of sums over 1 over alpha to the 2k, where the alphas are the complex zeros of zeta. So for example, one of the values he got was when he sums 1 over alpha to the 10, and he could show that this sum has to be equal to this value. It's a small value, but at the same time, using the 15 zeros he had approximated, he could argue that if he missed a zero, or actually, you know, starting with the using even the first 10 zeros he had approximated, so the zeros of height less than or equal to 50, if he missed a zero, then this missed zero would have to contribute a quantity of this size, 2.048 times 10 to the minus 18, which would contradict the value he computed for the sum over alpha. Right, and using this kind of argument, he could actually show that the Riemann hypothesis holds for the first 15 zeros, and all these are simple. Right. The issue with Graham's method is that it becomes really impractical to use it if you want to verify the Riemann hypothesis for higher and higher zeros. So for zeros with larger and larger ordinates, because the sum over the alphas, you know, decays very rapidly. So you need very, very high accuracy, which becomes impractical. So there was a major advance in about 1911, 1912 by Backlund, who gave a much more practical method to verify the Riemann hypothesis. And he could use his method to, basically his method consisted of 2 stages. In one stage, he would compute exactly the number of zeta zeros of less than a given height. So he could compute exactly that there are 29 zeros of zeta of height less than 100. So this would be the first picture. This would be the first picture here. And he could compute that there are exactly 79 zeros of zeta of height less than 200, which is the second picture here. So you see 78 appears, but the 79 is because there's a +1. And the Backlund method for computing these values is by the argument principle. If he could show that the real part of zeta, as he moves, the real part of sigma plus it as sigma moves between 2 and 1/2 remains positive, this shows that the argument of zeta by the time sigma is 1/2 has to be between minus pi over 2 and pi over 2. And using this, he could show that he could compute the n of t, the function that counts the zeros of height less than or equal to t. He could compute it because then he could express n of t in a simple form. Right, so this was the first part of the Backlund method, which is to actually compute n of t by hoping that the real part of zeta remains positive as sigma changes. And then in the second part, he uses the Lindelöf method, which detects sign changes, and he finds the expected number of sign changes. So up to 100, he could find that there are 29 sign changes, and therefore he found all the zeros of zeta less than or equal to 100. And same thing up to 200. So he could verify the Riemann hypothesis and the simplicity of zero up to these heights. Right, so this was this was a very important advance. It gave a practical method to verify the Riemann hypothesis, and the computations were completely rigorous and a true verification of both the Riemann hypothesis and the simplicity of zeta zeros. And a little bit over a decade later, Hutchinson extended Graham's computations so that he could verify the Riemann hypothesis for the first 138 zeta zeros. So which would cover the zeros up to height less than or equal to 300. And Hutchinson here did not come up with a new method. Instead, he simplified and explained existing methods by Graham, Lindelöf, and Backlund. And one kind of difference in his computations, which went higher than ever before, is that he used a kind of a mechanical computer to help with the numerical calculations. And he also emphasized one thing, which is when searching for zeta zeros, one could search for them between special points called Graham points, which were introduced by Graham in 1903 in his second attempt. And so the Graham, this would work better than like just simply stepping through the integers like Lindelöf did. So when Lindelöf looked for sign changes and for zeta zeros, he would just compute at consecutive integers and see if there's a sign change. There's no special reason to pick the sequence of integers here. And Graham pointed out that one could have a much better luck with these special points called Graham points, that they have this property that they tend to interlace with zeta zeros. Right. And there was the next advance, which was in 1935. Actually, it was in 1932 when Siegel discovered the Riemann-Siegel formula. But the issue is that you could not use the Riemann-Siegel formula directly to compute numerically with zeta, because there was no explicit bound on the error term in the Riemann-Siegel formula. So the important progress was in 1935 by Titchmarsh, who obtained an explicit estimate on the error term in the Riemann-Siegel formula, which is this bound on R in this picture. And this allowed Titchmarsh to use the Riemann-Siegel formula to compute with zeta. And he was able to go up higher than before, because to compute at height around T using Euler-Maclaurin summation formula, one would need to include about T terms in the sum. Whereas using the Riemann-Siegel formula, one needs to include only about square root of T terms. So it's, you do computations with about T terms or about square root of T terms. Square root of T terms would be much smaller when T is large. And this gave a big advantage. And this way, Titchmarsh was able to verify both the Riemann hypothesis and simplicity of zeros for the first 195, which covered T up to 390. Right. And then the following year, which was in 1936, Titchmarsh came back to the same problem with computing zeta zeros and extended his computations. He used more powerful mechanical computers. Here are some pictures of some of the mechanical machines that he used for the computations. And he was kind of helped by an astronomer, Comrie, in these computations. And Titchmarsh still used the Riemann formula and his explicit estimates for the remainder term in the Riemann formula, as well as a variation on Backlund's method, and searched for sign changes between gram points. So he kind of combined all these components that had been developed in the decades before. And he concluded, and this is kind of the picture here, is that the Riemann hypothesis holds for the first 1041 zeta zeros. And that this covers the range 40 up to 1468. And actually it must be that Titchmarsh missed a zero, because there are actually 1042 zeta zeros in that range. I'm still searching where the error happens in Titchmarsh paper in 1936, but he definitely went further than anyone before him and covered the Riemann hypothesis for the first 1000 zeros. Okay, so that's the end of my talk. Thank you very much.
Thank you, Ghaith, for the very interesting talk. I'd like to open the door for the questions now. Anybody would like to ask a question?
So I have a question. First of all, Shukran, thank you for the very nice talk. Of course, now we think of the zeta function as the first example of a Langlands-L function, and you could try to do such computations for other Langlands-L functions. I saw David Farmer listening, who probably has done that. And perhaps you've also thought about that. And I'm wondering, did any of these folks, I mean, certainly Dirichlet L functions were around, did they actually think about trying to do similar investigations for other Langlands-L functions? Or the L function attached to the Ramanujan delta function, to their tau function? Did they ever think about that?
I think at that point, like during the period that I covered, which was basically 1730 up to 1930, all the computations that I found were with zeta. The progress on other L functions was with basically generalizing Riemann's exact formula for pi of x to sums of other, but not actually with computing them. So I think the focus at that point was, computationally speaking, was on zeta.
Great, thank you.
Any other question for our speaker? Okay, thank you. Thank you very much, guys, for the talk.
Thank you.
And thank you all for attending. Please encourage your students next time to attend as well. We'll be having several public talks in the coming academic year. And we'll be in touch. Thank you very much.
Thank you very much. Thank you.